Hello, everyone. We're going to go ahead and get started on section 4.6, which is modeling with exponential functions. So in our last sections, we worked on equations with exponential functions, and we learned what exponential functions are. So now we're going to do some modeling or some real-life application problems with exponential functions. So as an overview, many occurrences that happen in nature can be modeled with exponential functions. So examples of these processes are doubling time, relative growth rate, radioactive decay, and Newton's law of cooling. Here's my cat. She wanted to be in the video. All right, so we have some radioactive growth or radioactive decay right about there. We've got some population growth, and we've got Newton's law of cooling off on a hot day, or more likely going to be a turkey on Thanksgiving comes out of the oven and you want to know how fast it's going to cool down. It's probably the most classic type of question there is for Newton's law of cooling. All right, so first we have exponential growth doubling time. If the initial size of a population is n naught, that is normally how we will say this symbol right here. It's with an n with a little subscript of a 0. So we say n naught to, say that symbol there. And the doubling time is a, so some amount of time a. And the size of your population at time t would be n of t is equal to n naught times 2 to the power of t divided by a. So the n naught is going to be the initial size of a population, or how much is in a population originally. And then we have it's going to double every so often or some amount of time, where the doubling time is going to be the value of a. A and t are both measured in the same time units, minutes, hours, days, years, etc. So this is for doubling time. If you have tripling time as well, the only thing that really changes is going to be the 2 would become a 3, and a would be the tripling time instead. So you may, run into a problem like that in your homework where you have tripling time, and so that would be the case for a problem like this as well. This is most often described with bacteria growth. So starting off with, 1 bacteria, and you've got 2, and then 4, and then 8, and 16, 32, 64, it goes on pretty quickly. So bacteria growth is usually what is used for exponential growth with doubling time. We are going to have another type of exponential growth, which is used a lot more often. So when you use doubling time, it is very specific to the amount of time it takes for something to double or triple is this amount of time, so on and so forth. So we're going to see the two differences after we do an example using exponential growth doubling time. So example 1, we say under ideal conditions, a certain bacteria population doubles every 3 hours. And initially there are 1,000 bacteria in a colony. How many bacteria are in the colony after 15 hours? So let's go ahead and go on over to our notes to work on example 1. All right, so we have our first example, exponential growth using doubling time. Here's our equation, n of t is equal to n naught times 2 to the power of t divided by a. We said that n naught was 1,000. We're starting off with an initial bacteria population of 1,000. We said that the doubling time was 3 hours, so it would take 3 hours for your population to double. And then we say how much is in the population, or how much bacteria is in the population when t is equal to 15. So we have all these details written out here. We're going to take all of our values and plug it into the formula for exponential growth doubling time. So this means that n of time t, where t is 15, so this is really n of 15. This means the amount of population of bacteria after 15 hours. This is equal to n naught, which we said was 1,000, times 2 to the power of t, which is 15, divided by a, which was 3. So we have 1,000 times 2 to the power of 15 over 3. We can simplify that a little bit. 15 divided by 3 is 5. So n of 15 is equal to 1,000 times 2 to the power of 5. So we can keep solving for this. N of 15 is equal to 1,000 times, and 2 to the power of 5 is 32. So N15, or a population after 15 hours, is equal to 1,000 times 32, which means that it is 32,000. And there we have it. So population after 15 hours would have been 32,000 bacteria in our population, which, if we're starting with 1,000, 15 hours, that's quite a bit. That's less than a day. You would have gained 31,000 bacteria in a population. So, all right, let's go ahead and go on back to our lecture. All right, so that was example 1, which just finished up. Now we can move on to exponential growth, which is known, this one is also known as the relative growth rate. So this is the one that is used much more often than doubling or tripling time. So if we use the base E in an exponential model, you can get a population model in terms of relative growth rate instead of doubling or tripling time. And this is just because not everything doubles or triples in a specific amount of time. A lot of time it's going to be relative to certain factors in the environment, and so it's better to use a relative growth rate instead of doubling or tripling time. So with exponential growth, or the relative growth rate, we have a population that experiences exponential growth, increases according to the model. N of t is equal to n naught times e to the power of r times t. So n of t is the population at time t. N naught is that initial size of your population. R is the relative rate of growth. This is expressed as a proportion of the population, so it can be a percentage, decimal, anything along those lines. When you do your computations, you want it to definitely be in decimal form. So if you're given it in percentage, you would need to change it. And then t, where t is time. So this is the equation that we are going to use. And if we notice something here, when we learned about continuously compounded interest, we said we had a principal, or an original amount, times e to the power of rt. And this is the same equation, actually. So this is the same equation as continuously compounded interest. It's just that n naught is now the initial size of a population instead of an initial amount of money. All right, so this is the equation that we're going to use for example 2. So example 2, a small lake is stocked with a certain species of fish. The fish population is modeled by the function p equals 14 divided by 1 plus 4 times e to the power of negative 0.7 t. P is the number of fish in thousands. That is an important fact. And t is measured in years since the lake was stocked. So A, find the fish population after 5 years and round to the nearest whole fish. And B, after how many years will the fish population reach 2,000 fish? Round your answer to 2 decimal places. So 2 things that's important before we get started on this problem is knowing that P is already in thousands. So whatever number that we have for P, we need to translate that so that it already has the thousands kind of taken into consideration. So this is, for example, in part B, where we say the fish population, we want to know when it reaches 7,000. Well, P, the population, is already in thousands. So you would write 7 instead of 7,000 because P is already inherently in thousands. Then another thing to kind of look out for is making sure to round your answers when necessary. Also, when talking about a fish population, you do not have half of a fish. That fish, it would probably technically be dead. So no half fish, no quarter fish, no 3/4 fish. It is a whole fish. You round to the nearest whole number. So a lot of times context is very important for problems like this. Just in the sense that if you have a living thing, you do not have half that living thing. So another thing to remember about this problem. So all right, let's go ahead and go on over to our notes to solve the problem. All right, so example 2, we have our population equation here, 14 divided by 1 plus 4e to the power of negative 0.7 t, where p is in thousands. And for A, we want to know how much is the population going to be after 5 years. So that means that for our problem, we want to know what is p when t is equal to 5. So we'll go ahead and plug in 5 for t and find what our population is going to be. So we've got population is equal to 14 divided by 1 plus 4e to the power of negative 0.7 times 5. Now, by all means, for a problem like this, you would definitely want to use a calculator. So we could use a calculator to do this problem. Let's go ahead and pull up our TI-84. All right, so we had 14 divided by, and since we are dividing by an expression in the bottom, we definitely want to have parentheses in this case. So we're going to have parentheses 1 plus, and we're going to have another parentheses, 4 times e to the power of negative 0.7 times 5 on to the next line here. All right, so we've written in all of everything. So this is the parentheses for the exponent of e, the parentheses for 4 times e to the power of negative 0.7 times 5, and one more parentheses to finish off the denominator. So we press enter and we get 12.49119445. All right, so what we wanted to do was round to the nearest whole fish. What we have here is the number 12.491 if we round to 3 decimal places. And so, like, oh, okay, 12.49, that's probably what, like 13 fish? Remember, population is already in thousands. So what we have here is 12.491 thousand, which essentially means that we can take our answer and multiply it by 1,000. And if we multiply this answer by 1,000, we get 12,491.19445 fish. But remember, we want to round to the nearest whole number, so this would be 12,491 fish. So, all right, that's how we put those computations into our calculator. Let's go ahead and go on back over to our notes to write this in. All right, so we found this value. It came out to about 12.491. And then remember, we had to multiply by 1,000. This is because population is in thousands already. And so this answer tells us 12,491 fish. All right, so that's how many fish were in the population after about 5 years. For part B, we need to know the time it takes for our population to get to 7 years. Sorry, 7,000. There we go. There was a 7 in it. So for part B, we're saying that the population we want to be 7,000. But remember, it's already in thousands. So if we're saying that the population is 7,000, we're really just going to write 7. We could put in some parentheses, 1,000. So when we write out our equation, we're going to write 7 instead of our population P. So we'll have 7 is equal to 14 divided by 1 plus 4e to the power of negative 0.7t. So this is what the value that we have right now. And so in this case, what we're looking at is that we want to solve for time. And time is an exponent on e in the denominator. So we want to rearrange this problem and manipulate it as much as possible so that we have e by itself with t in the exponent. Because once we have that, we can take a natural log of both sides and solve for t. But we want the exponential expression alone by itself on one side. So what we can do is multiply each side by the denominator. So multiply by 1 plus 4e to the power of negative 0.7t on both sides. This will end up giving us 7 times 1 plus 4e to the power of negative 0.7t is equal to 14. Then we can get rid of the 7 by dividing each side by 7. So in this case, 14 divided by 7 is 2. So we'll have 1 plus 4e to the power of negative 0.7t is equal to 2. Then we can get rid of the 1 by subtracting 1 from both sides. This will give us 4e to the power of negative 0.7t is equal to 1. And then last thing, because we want that exponential expression just by itself, we don't want the 4. So we're going to divide each side by 4. This finally gives us e to the power of negative 0.7t is equal to 1 over 4. So now that we have this written out, what we can do to get rid of the value of e and bring that exponent down to the front, or just down from the exponent's place, is to take a natural log of both sides. So we're going to go ahead and take the natural log of both sides. We'll have the natural log of e to the power of negative 0.7t is equal to the natural log of 1 over 4. So the natural log and e are going to cancel each other out, and the exponent will come out of the exponent's place and come down into just, I guess, the normal space. So in this case, we'll have negative 0.7t is equal to the natural log of 1 over 4. We're solving for t. The last number in front of t is negative 0.7. So we'll divide each side by negative 0.7. And we get finally that t is equal to the natural log of 1 over 4 divided by negative 0.7. We want to round this to 2 decimal places. So we want to solve this. We can plug this into our calculator. It's a little simpler than the last one. So I trust that you can put this in your own calculator. And we should get that this comes out to about 1.98 years. Round into a nearest whole number. This is really just about 2 years, but since we were rounding to 2 decimal places, that means that we would leave it at 1.98 years instead. So, all right, that wraps up example 2. Let's go on back to our lecture. All right, so that was example 2 we just finished up. So moving on, next we have radioactive decay. So the rate of decay is often expressed as a half-life, or the time it takes for a substance to decay to about half its original mass. A half-life is not literally half of something's life. The half-life is just the life amount that it would take, or the time it would take for an original substance to become half of what it originally was. That is a half-life. So just because you're given a half-life does not mean that 2 times the half-life is its whole lifespan. That is not true. So just remember that half-life is the time it takes for a substance to become half of what it originally was. So for a radioactive decay model, we say if m naught, so now we have m naught, is the initial mass of a radioactive substance with a half-life of h, then the mass remaining at time t is modeled by this function. M of t is equal to m naught times e to the power of negative r times t, where r is the natural log of 2 divided by h, and it is the relative decay rate, and h of t are measured in the same time units. So this is our function here. Our rate we can always find by taking the natural log of 2 and dividing by h, as long as we know the half-life. This is not the same as for what we saw for our exponential growth. So even though in this case we do have an equation for rate, we do not have that same equation for exponential growth. This only works for radioactive decay. So in this case, we can find the rate without really doing any hard searching. We have a formula for it. So typically what would be asked for is to solve for time in problems like these. So, all right, this is the equation that we're using. Let's go ahead and do an example. For example 3. We have a wooden artifact from an ancient tomb contains 60% of the carbon-14 that is present in living trees. How long ago was this artifact made? We say the half-life of carbon-14 is 5,730 years. We want to round our decay rate, R, to 8 decimal places so we can get as accurate an answer as possible. And then we're going to round our final answer to the nearest whole number. So, all right, we've been given quite a bit of information here, but knowing how to use it is going to be the important part. So let's go ahead and go on over to our notes so we can work out this problem. All right, so with example 3, we have our radioactive decay equation here. M of t is equal to m naught times e to the power of negative r times t. R is the natural log of 2 divided by h, where h is the half-life. We say that h, or our half-life for our problem for carbon-14, is 5,730, and our m of t, or the amount after t amount of time, we would have is 60% of the original amount. So if we still have 60% of the original amount, that means that our m of t is really 0.6 times m naught. So 60% of something, you could put the 60% into decimal, which would be 0.6, and you can multiply it by whatever factor you have. So we had 60% of m naught, that would be 0.6 times m naught. So we can go ahead and we can plug these values in. First thing we kind of want to figure out though is the rate, because if we plug everything in that we have now, we don't know what R is, but we do know the half-life, so we can go ahead and we can find R. So R is equal to the natural log of 2 divided by H, which we said was 5,730. So that's where the H is kind of going here. And we want to use a calculator to find this value. And we're going to round to 8 decimal places. We want to keep it as accurate as possible. When it comes to exponential functions, it's always important to be as accurate as possible, just because even the slightest little difference in an exponential function can really mean huge differences in your answers. Even, a difference of 0.01 could be the difference of like 20 in your answer because they're exponential. So they increase extremely quickly or they decrease extremely quickly. Either one, whether you have radioactive decay or exponential decay. All right. So we can put this into our calculator, natural log of 2 divided by 5,730. I trust that you can put this in your own calculator. Rounding to 8 decimal places, we would have 0.0001209.7. And yes, that is 8 decimal places. So that's the value that we should end up getting for R. So plugging the value of R into our original equation, this will now allow us to find T, which is what we wanted. How long will it take for us to have 60% of the original amount? So plugging this all into our equation, we had that m of t was really 0.6 m naught. So we'll write 0.6 m naught is equal to m naught times e to the power of negative 0.0001209.7 t. So looking at our equations here, we have an m naught in both sides of our equation. This essentially means that we didn't need to know how much we actually had originally in our substance for our carbon-14. We just needed to know that it was 60% of the original, and we actually don't really care what the original was. Since m naught is in both sides of the equation, we can go ahead, we can divide each side by an m naught, and we get canceled on both sides, leaving us with 0.6 is equal to e to the power of negative 0.0001209.7 d. So we actually didn't really care to know what the original amount was. We didn't necessarily need to. But now that we're at this point, we have our exponential function isolated to one side, so we can go ahead and we can take the natural log of both sides. This would give us the natural log, and I'm going to switch the sides as well, of e to the power of negative 0.0001209.7 t is equal to the natural log of 6, or 0.6, there we go. And so what we see here is that the natural log and the e will cancel each other out, and the exponent comes out to the front. So this becomes negative 0.0001209 t is equal to the natural log of 0.6, whatever value that is. And remember, we're solving for t. So if we want to solve for t, we can go ahead and we can divide by that negative 0.000120097 number. And it cancels out on the left-hand side. Thank goodness we don't have to say that anymore. All right. So this means that t is really equal to, well, one more time, the natural log of 0.6 divided by negative 0.000120097. Whew. And we want to plug that into our calculator. And when we do, we want to round to the nearest whole number. In this case, we want to find how many years this is going to take us. By all means, we plug this into our calculator to find this value. I trust you all that you know how. And the answer we get is 4,223 years. Which, if we think about it, it would take our carbon-14 5,730 years to become 50% of the original amount. So we had a little bit more than 50%, which means that we had a little less than 5,730 years. So there we go. That is how long it would take for carbon-14 to decay to 60% of its original mass. So, all right, that wraps up example 3. Let's go ahead and go back on to our lecture. All right, that was example 3. So moving on, we have our last exponential type of application here. We have Newton's law of cooling. So Newton's law of cooling, we say if T naught is the initial temperature of an object and its surroundings have temperature T sub S, then the temperature of the object at time T is modeled by this function. T of T, or the temperature of the object at time T, is equal to T sub S, the temperature of the surroundings, plus T naught, or T initial, minus the temperature of the surroundings, times e to the power of negative kt, where k is just some positive constant that depends on the type of the object. So this is the equation. We have a picture of a turkey cooling down. This is the most common type of problem that you will see with Newton's law of cooling. It's always kind of set up in like it's Thanksgiving dinner and you're taking your turkey out of the oven, and how long is it going to take to cool down to about this much, and things like that. So this is also actually used a lot in forensics, in modern day forensics as well, to find out. It's a little bit morbid, but to find out how long ago, a person may have been killed based on the temperature of their body. So fun fact, but it is used in modern day forensics, and things like that, which is kind of cool and a little dark. But all right, we're going to go ahead and do our next example, which is a roasted turkey was taken out of the oven. So example 4, roasted turkey is taken from an oven when its temperature has reached 185 degrees Fahrenheit and is placed on a table in a room where the temperature is 72 degrees Fahrenheit. A, if the temperature of the turkey is 145 degrees Fahrenheit after half an hour, what is the temperature after 45 minutes? Round your answer to the nearest whole number. And B, after how many hours will the turkey cool to 100 degrees Fahrenheit? Round your answer to 1 decimal place. So for part A, it's not entirely clear yet, but for part A, we want to be finding the value of K in our equation. For part B, we want to be able to find the value of T in this specific instance. So, all right, we've been given a lot of information. Let's go ahead and go on over to our notes to solve this problem. All right, so for part A in this problem, we have our Newton's law of cooling equation. T of T is equal to T sub S plus T sub 0 minus T sub S times e to the power of negative kt. So we said that T sub S, the temperature of the surroundings, was 72 degrees. And T naught is the temperature of the turkey right as it comes out of the oven, which is 185 degrees. And then for part A, we said that the temperature of the turkey was 145 degrees when time was 30 for 30 minutes. So we're going to use this information, and what we're going to do is we're going to find the value of K, because we want to know what is T of T when T is 45. So we're given this information, but we want to know what is T of T when T equals 45. So we need to find the value of K in this case. So all right, we're going to plug all of these values into our equation. So T of T is going to be 145. T sub S is 72. T naught is 185 minus 72 times e to the power of negative k times time, which is 30. So we said 30 minutes, our temperature of our turkey was 145 degrees. So we have to use 30 for T. All right. So this is our equation. We want to simplify down as much as possible. So we want to simplify the exponential equation first. So we can go ahead, we can subtract 72 from both sides. We want to start chipping away at our functions here. So this would give us 145 minus 72 would be 73 is equal to 185 minus 72 would be 113. This is the power of negative, we can say negative 30k. You could still have it say negative k times 30 if you'd like. There's really no difference since it's multiplication in this case. But all right, so now we want to isolate E as much as possible. So we can go ahead and divide each side by 113. There we go. So this ends up giving us e to the power of negative 30k is equal to 73 divided by 113. Now you could divide 73 by 113 if you'd like. If you do, always remember to keep a lot of decimal places so that you can have an accurate answer in the end. You never want to round in the middle of your problem, especially not to like 1 or 2 decimal places. Definitely not. If you want to find a decimal value and you have to round somewhere in the middle of your problem, keep as many decimal places as possible. So we're just going to leave it as 73 over 113 in this case. But all right, so we have e on one side. We know that the only way to get rid of the e and bring that exponent down to the front is to take the natural log of both sides. So we're going to go ahead and take the natural log of both sides of our equation. The natural log and e cancel, and our exponent comes out to the front. So this problem here, we're going to have negative 30k is equal to the natural log of 73 divided by 113. We want to solve for k, so we can get rid of that negative 30 by dividing by negative 30 on both sides. This gives us that k is equal to the negative natural log of 73 divided by 113 divided by 30, which we want to find the value of k. We want to round to, let's go 6 decimal places. That's not in the problem already. So we get k is equal to about 0.014564. All right, so we found the value of k, which is what we need to solve for our next part, which is what is the temperature when time is 45 minutes. So now we know the value of k, we know our constant value, so we can go ahead and we can use that in our equation. So we got to kind of plug everything back into the original equation, which is T of T is equal to temperature of the surroundings, 72 degrees, plus initial temperature minus temperature of the surroundings, times e to the power of negative kt, so negative 0.014564 times t, which is 45. So we're going to go ahead, we're going to plug in this number. We want to round this to the nearest whole number in this case. So using our calculators to plug this in, we go ahead and we find that this is equal to about 131 degrees Fahrenheit. So that would be the temperature of the turkey after 45 minutes. It would be 131 degrees Fahrenheit. So we can add that in. After 45 minutes. That doesn't even look like a word. Let's erase that. There we go. So, all right, that was part A. We wanted to know what was the temperature of the turkey after 45 minutes. Now for part B, we want to know how long it's going to take us to get our temperature of our turkey to 100 degrees. So that's what we'll do for part B. So a lot of these values are still the same. The time or the temperature of the turkey is 185 degrees. The temperature of the surroundings is 72 degrees. And now we have the temperature of the turkey is 100 degrees. And we know the value of K. K is 0.014564. And so what we're looking for here is T time. So we're going to plug everything into our formula. So we'll get that 100 is equal to 72 plus 185 minus 72 times e to the power of negative 0.014564 t. So we want to simplify this as much as possible. So starting off, we can get rid of that 72 by subtracting it from both sides. Then we get 100 minus 72 is 28. And 185 minus 72 is going to be 113 times e to the power of negative 0.014564 t. All right, we want e to the power of that exponent all by itself. So in order to do that, we want to get rid of the 113 in the front. So we can divide each side by 113. This is going to give us, and we're going to flip the sides as well here, e to the power of negative 0.014564 t is equal to 28 divided by 113. Now we have e to one side, a fraction on the other. To get rid of the e, we can take the natural log of both sides. So we can take the natural log of both sides. Natural log and our e cancel each other out. And that exponent is going to come out to the front. So we'll end up getting that negative 0.014564 t is equal to the natural log of 28 divided by 113. And so we want to solve for t, so we're going to get rid of that decimal in the front there. So we can divide each side by a negative 0.014564. This will tell us that t, or our time, is going to be the natural log of 28 divided by 113, all divided by negative 0.014564. Last time we had to write that. We want to plug this number into our calculators. We're going to round to the nearest minute or one decimal place for hours. So if we find this value, this is going to come out to about 96. But remember, this is in minutes. Ooh, minutes. So we get that this is 96 minutes, but the question was asking us how many hours? How many hours is it going to take for this to happen? So we have 96 minutes. We want to convert this into hours. So 96 minutes. There are 60 minutes in 1 hour. So we're going to divide by 60. Those will cancel, and 96 divided by 60 gives us 1.6, and this is going to be in hours. So The answer in hours was 1.6 hours it would take for the turkey to cool down to about 100 degrees, or 96 minutes if you're looking for minutes instead. So that is how we would do that problem there. These two tend to be a little bit longer for Newton's law of cooling. So, I imagine that you would definitely break this equation out to find out when your turkey will be cool enough for you to eat on Thanksgiving Day. I'm sure of it. But yeah, these do tend to be a little bit longer, just because you have to find the value of K, and then you also are required to find the value of T for a problem like this. But all right, so that wraps up example 4. So let's go on back to our lecture. All right, so that was example 4, and that does wrap up section 4.6. So in section 4.6, we learned about exponential growth for doubling time, exponential growth for relative growth rate, radioactive decay, and Newton's law of cooling. So, all right, that wraps up section 4.6, and I'll see you in the next one.